Good evening. Welcome again to this Developmental Artificial Intelligence lesson. So let me begin with a small reminder of what we said last week. I gave a full theoretical presentation about what we are trying to do. So we are trying to learn, that is, discover, organize, and exploit regularities of interactions in the agent's experience of interaction with its environment. So we create an agent which interacts with its environment, and so there exists regularities in its interaction, and the agent has to discover them, to organize them in memory in some way, to be able to exploit them and exploit them for its own good, that is, for surviving and develop smarter behaviors and so on. And we want to do that, as I said, without pre-encoded ontological knowledge, that is, without encoded knowledge that we have about the agent's environment. So the agent must discover its environment by itself. Why do we do that? Because, for example, if we want to design robots that interact with the real world, we won't be able to encode all the knowledge about the environment. So we need an agent that discovers knowledge by itself. So that doesn't mean that we do not encode any knowledge about the environment. It only means that we don't encode what we call ontological knowledge about the environment. But we encode presuppositions about the interaction. So those presuppositions are about the agent's possibilities of interaction with its environment, but not about what entities exist in this environment. So what we want is a form of constitutive autonomy of the agent. That is, if we have the same algorithm from the start in two identical robots, we want that each of them develop different behaviors depending on their own individual experience of interacting with the world. So to manage to do that, there is a key notion that I introduced, the notion of self-programming. Self-programming is when data that is learned by the algorithm is executable data. That's the main difference between what we are doing in this course compared to most machine learning algorithms in which learn weighted values that allow the system to adapt but not to learn executable data, that is, not to learn new behaviors. That is really the specificity of this course. So today I will reuse some examples I presented last week, and then I will present more precisely how we can translate this theory into the algorithm. So it's mostly a problem of sequence abstraction, find regularities in time in sequences of interaction, and abstract these sequences in order to reuse them. So we developed a mathematical formalism that I will present called radical interactionism. That is, use interactions as the primitive properties of the algorithm. And then we'll continue the exercise how to implement your own self-programming agent. So let me remind you what we saw last week. So we develop agents that will choose from amongst the possible experiences that they can perform in the world. Here we have 6 experiences, and they receive a result from this experience. So for example, this triangle is moving forward, and it may work or not work. If it doesn't work, the agent receives 0, and if it works, the agent receives 1. And those experiments can change the state of the world. For example, the agent will move in the world. And we think in terms of interactions. So an interaction is the association of an experiment and a result. And there are regularities in interactions. For example, it observes that if it enacts interaction I8, then it is likely that it can again enact interaction I8. Those regularities are increasingly complex. So, for example, after enacting this whole sequence of interaction, it is likely that it can again enact this subsequent sequence of interaction. So let me play again the example. So it picks its interactions, it doesn't know what they mean. And what we see is that after a while, so let me remind you, so those interactions corresponds to touch in front, to the right or to the left, and when it touches, the square flashes yellow. Those interactions corresponds to turning to the left and right, and those interactions consist of moving forward. So after a while, it learns that it should touch in front before moving forward and not move forward if it touches a wall. And then if it touches a wall, it should touch to the left and to the right. And then if it touches empty to the right, it should turn right, and the same to the left. So what is crucial here is that we did not implement this strategy, and we did not tell that some interactions could be used as a perception. Instead, the agent discovers by itself that some interactions can be used as a perception to inform it about its context. So do you have any question, or so it's okay, you remember this from last week? So it raises a problem about how do we validate those agents. So it looks like a maze, but it's not a maze because there is no final objective to reach. So we cannot evaluate the algorithms in terms of their performance in reaching final objectives, because we don't have a final objective. We don't implement agents that have a final goal to reach. Instead, what we want is that the agent's behavior organize so that it looks intelligent when we look at it. So that leads us to develop an assessment paradigm that is different from traditional assessment paradigms in machine learning. In our case, we are assessing our algorithms through behavioral analysis. So we analyze the agent's behavior and we demonstrate that intelligent behaviors emerge. So to do that, we show activity traces like this one. So this trace represents the agent's behavior. So it's organized in tapes. here is from step 0 to step 500. So here are the first step is the primitive interactions. Here the second step is the value of interactions. So in red it's negative interactions, and green positive interactions. So here we see that we have a lot of negative interactions, and then after a while, so it takes about 200 steps. So we see that there is less and less red interactions and more green interactions. There still is negative interactions because it is obliged to enact negative interactions in order to be able to enact positive interactions, but we see more positive interaction. And that's not the only aspect that interests us. The other aspect that interests us is its capacity to develop behaviors that consist of engaging in sequences of interactions willingly. So that's shown by the third step here in gray and black. It's a little bar graph, and when it's on the second level, it means that it makes the two subsequent interactions willingly. So here, for example, it enacts touch forward then move as a whole sequence, as a two-step sequence, knowingly of what it is doing. And when there is a black segment here, it means that this intended sequence of interaction is interrupted because the agent failed to predict the results of its experiments. So the highest the bar graph in this third step, and the longer the intentional sequences that the agent tried to enact. So here is a third level sequence: turn right, touch forward, move forward. Here again this third level sequence, and then it learns longer and longer sequences as he learns to control better its interaction with its environment. So in the exercise, I am going to ask you to show activity traces. So I'm not asking you to show those graphical representation, but just to display traces on the console. And we're not going to be able to implement such an elaborated agent, but we will begin with a simpler agent. So this algorithm can be implemented in a robot. So it's exactly the same algorithm with the same possibilities of interactions. So this robot is an epoch robot. So when the LED flashes here, it means that it uses a sensor, an infrared sensors, here to the left, here to the front, and detects a wall. But it doesn't know what it means. To the left, to the right again, in front, to the right, to the left. Up he bumps into the wall, and then turns. So it bumped twice. So it turned. So it's exactly the same algorithm, but we don't have such an elaborated behavior as in the small loop. But what we show is that quite quickly it learns to use its infrared sensors, the equivalent of touch, to detect if there is a wall, and if there is no wall, it moves forward. If there is no wall, it moves forwards, and if there is a wall, it turns. So test forward, turn, test left, test forward, move forward, test forward, move forward, detect wall, turn, detect something, turn, detects nothing, move forward, detects wall, detects a wall, detects nothing, move forward, detects nothing, move forward. So here it has roughly understood that it should use its front sensor before moving forward, and if it detects a wall, it should turn. So it's the same algorithm. It's just to show that it works the same in robots. So you might expect in the simulated environment that it's simple because the environment is discrete, but in fact the algorithm works the same if the environment is not discrete, is a continuous space like the real world. And also it works in spite of the fact that there is noise in its sensors, so sometimes there are false detection or false alarm, but the algorithm can resist this noise. So it obliges to think differently when we design a robot. So for example, it will be easy to encode this behavior, to hard code this behavior, but that's not what we want to do. So we have to set different objectives in what we want to do in our robots and design it differently. For example, we had to adjust the range of the sensor to a distance that is close to the distance that it covers when it moves one step forward, so that its sensor is useful to inform it of the presence of the wall on the range of its possibility of displacement. So it can use its sensors. If the sensors had, for example, a wider range of detection than each move forward steps, then the sensors would be useless, and it would learn not to use them and just try to move forward and bump into walls. So how can we implement systems that will develop even more sophisticated behaviors in more complex environments? So I showed you this example in which there are different kinds of objects in the environment. There are those color bricks of walls, and there are those flowers here, but the agent cannot feel the difference, cannot detect the specificity of these objects. So the color bricks feel exactly the same as the walls, and the flowers feel exactly the same as a blank cell. So it shows that the agent can in fact go into an infinitely complex world, because in fact they ignore the complexity of the world. They only see a certain level of complexity, and they develop the behavior that they can with their possibility of representing this world. So the problem is not to develop agents that can deal with more complex environments per se, because they are already able to interact with complex environments. But the problem is how to develop smarter behavior and make them aware of more complexity in the environment. So how do you think we can do that? So what would you like to do from that? We see that it's still quite limited for the moment, so how to improve that? Yes, so discover longer sequences of interaction. So yes, we could place the agent in a problem where there are longer sequences of interaction, and we could expect the agent to learn those sequences. But in the problem that I just showed you, if we leave the agent longer, he can discover longer sequences. But we don't know how to design a problem that would offer longer sequences. But if we could design such a problem, we expect that our current version of agent could learn longer sequences. So here it's more a question of designing another problem that has longer sequences of interaction, that affords longer sequences of interactions, to demonstrate that the agent is able to learn such long sequences. So yes, increase the length of sequences. Other ideas?
Donc en fait, ça revient à implémenter une forme de motivation plus compliquée.
Yes, so implement other forms of motivations, more complex forms of motivations. So for example, implement some form of boredom, and if it detects that it always makes the same sequence, then we could implement a mechanism that forces the agent to try something else. Yes, increase the number of possible interactions. So currently we have only 10 possibilities of interactions, and we could increase this number. So that's something I was expecting you to say. So increase the complexity of the relational domain. So far we have only those 10 interactions, and what happens if we increase this set of possibilities of interactions? How will the agent deal with this increased relational domain? Yes, so increase the number of possible results. So we could either increase the number of possible experiments or increase the number of possible results. And in both cases, that will increase the number of possible interactions, because the set of possible interactions is the square product of the set of possible experiences and the set of possible results. So yes, if it can, for example, touch a flower in the previous experiment, we could return a different result from the experience of touching. So this will lead to different other questions. So for example, we would like the agent to find that when it have an interaction touching a different object, so like touching a smooth object, we would expect the agent to learn to recognize that this touching correspond to another form of object. And it's no longer a problem of sequence learning, it is a problem of learning the existence of objects or categories of objects in the world that could afford different possibilities of interactions. And it is related to the problem of learning the persistency of objects. So we could feel through touch a specific category of object and learn that this object is persistent in space and these objects affords a whole set of possibilities of interaction.
En fait, j'arrive à ce point-là qui est être capable de gérer.
So this leads me to another issue, not only interact with an environment that offers sequential regularities in time, but also learn to interact with an environment that affords spatial regularities of interactions. So to learn that there might exist persistent objects in space, and the agent would have to learn that those objects exist. And currently the agent learns this, but only implicitly. So here it's a purely sequential learning, but when we look at the agent from the outside, we see that it learns to associate spatially interactions. So it associates touching to the left with turning to the left. So implicitly, it seems that it understood that it exists in space, but this knowledge is purely implicit. And if we want to move forward towards an agent that is able to generate more complex behaviors in an open space environment, we'll need an agent that can shift from this implicit knowledge of space towards an explicit knowledge of space, so it can discover that some categories of objects are persistent and affords different forms of interactions. And currently it cannot do that because it has no means to discover that there are persistent objects in space. I hope this will become clearer when in the rest of the class. So currently I noted two directions. One is to increase the number of possibilities of interactions, and the other is to implement an agent that can discover spatial regularities of interaction. So to move towards this, we already found something. We tried a larger relational domain in which we have all these possibilities of interactions with values, and the agent ignores their meaning, but in fact those interactions are not only proximal interactions, but they are distal interactions. So it has a visual system, you can think of it as vision or smell, and it is sensible to objects that exist in its sensory field, and it is especially sensible to displacements of objects. So the objects are immobile, but when the agent moves, the relative distance of objects changes, and the agent can sense this displacement. So it can, for example, have an experiment consisting in moving one step forward, and if it moves closer to an object, then the result will be would indicate the fact that the object becomes closer to the agent. It is also sensible to the area to the left or in front or to the right in which the object is. So it's written here, area A, area B, and area C. So the squares are the experiment trying to move forward. If nothing changed in the visual field, it's a white square. If something appears in the visual field, then it's this light green square. If something gets closer in my visual field, it's this interaction. If something disappears from my visual fields, it's this gray square. If I move forward and I I step on an object and I eat it, this is this eat interaction, and if I bump into a wall, this is this red square. And if the agent turns to the left, if nothing changed, it's this interaction. If something appears, get closer, or disappears, it's these interactions. So closer when turning is moving from area C to area B. And it's the same when turning to the right. So here the relational domain is much wider. Although the number of experiments is reduced, there are only 3 possible experiments: move forward, turn left, or turn right. And because we give positive valence for an appearing object or moving closer to an object, and giving negative valence for the disappearance of an object, then we implement a motivation to move toward objects. But with this motivation, we did not implement a specific strategy. So the agent finds different possible strategy. So here the agent is constrained to a grid. So it can only move from cells to cells. And we observe 2 different kinds of behaviors. In this example, it learns to move in a staircase behavior until it is aligned with the object. And in the second behavior, it moves on a straight line, but it has to move 1 cell too far until the object is exited from its visual field, and then it has to step back 1 cell to get aligned with the object and then to move toward the object. So those are 2 possible strategies that the agent will develop from the motivation we gave it to move towards an object. So here's the demo. Here's the first in which it develops the staircase behavior. So at the beginning it does randomly, and then after a while it discovers the staircase behavior. So it's the same algorithm as before, which only learns sequences, but it develops behavior in space because its interactions are distal interactions rather than just proximal interactions. So we still have this self-programming effect. So it learns this behavior, and then we add a new object. It enacts always this same behavior. But the same agent, the same algorithm, in another experiment, just because the initial conditions are different, in fact it starts 1 cell below, so it develops another behavior. He tries other experiments. At the beginning, when it is fumbling, it discovers other experience, so it develops the other behavior. So here it developed the behavior consisting of moving too far, then stepping back 1 cell to get aligned with the target in order to reach the target. So here we see this self-programming effect well. That is, depending on its individual experience, it programs itself differently, and once it has programmed itself, it continues exploiting this behavior that he learned. So this shows well that we did not encode the strategy. Of course, it would be very easy to encode a strategy, like always move in a staircase or in a straight line. But we didn't want to encode the strategy. We want the agent to learn and discover the strategy by itself. So here we are quite happy because it models behaviors of self-motivation. So for example, we know that a newborn mammal, for example, naturally goes toward the milk of its mother, and we think that it does that because it climbs a gradient of smell, and that explains why it goes toward the milk. But it is not hard-coded. It does not know which movement it has to do to move to increase the smell. And at the beginning, it babbles, it chooses random behaviors, and after a while, it learns which behaviors allows him to move towards the target. So we think those mechanisms are primary in developmental learning by giving innate tendency, not because there is a reward. So it doesn't need to have reached the target before. It moves toward the target even before having even ever eaten the target. So it's a kind of reinforcement, but it's not reinforcement from reaching a predefined goal. It's just the implementation of behavioral tendencies to move towards objects. So similarly, this can be encoded into robots. So that's, again, the same algorithm. So the vision is implemented with the Kinect here at the top of the robot. And the target is this 2D code target. So it's exactly the same algorithm, except that, of course, it's more slower. But after a while, it finds the same behavior. When it turns, it does not turn of 90 degrees, but only about 30 degrees. So the different strategies are far less obvious here. But this is just to show that this algorithm can be directly transposed to a robot, because you just have to adapt the interactions, and the algorithm works the same because it doesn't need to know the meaning of interactions. It's just find regularities in sequences of interactions. Okay.
C'est ce qui nous a permis de développer cet exemple que je vous avais montré la dernière fois. Donc là, il faut regarder ces deux agents.
So that also this mechanism that allowed us to implement those agents. So here you have to look at these two gray sharks here. And of course it works as well when it's not constrained to fill a grid. It works in a continuous environment. So we can program it to go explore different scient objects. They also tend to move toward each other, so they like to get closer to each other, and so this generates this playing behavior. But what they don't know how to do is to bypass walls. So if a target is hidden behind a wall, they don't think of bypassing the wall. And that's something we would like to do in the future, implement agents that would understand that if they don't see a target anymore, that might be because the target is hidden, or so this, of course, is more than a maze-solving problem. The agent has to figure out that it's because there is something before the target that explains that it does not see the target anymore. So it has to interpret the different possibilities of perception to find out that if it doesn't see a target, it might be because it's hidden, it moved behind a wall. So it's not only constructing a map of the environment and solving a maze, it's about understanding and interpreting its sensory system to understand these kind of things. Understand that some objects are persistent, and even if you don't see them, that doesn't mean they don't exist. They might be hidden.
Les exemples là que je vous ai montré juste avant, c'était encore de l'apprentissage purement séquentiel. Donc en fait, c'est pour ça, en fait,
So the examples I showed you before were purely sequential examples, but here we had to implement something else. So the agent had to have a spatial memory of its surrounding. But I will stop here for today. I will talk more next week about implementing a spatial memory of the environment. But for now, I will explain deeper the details of the sequence learning algorithm. So what we want is that when there is a sequence of interactions that happen, the agent must find out that there are significant episodes. So here these interactions are represented by this triangle, green triangle that represents an episode. And it has to find those episodes hierarchically. So for example, this pink triangle is a sub-episode of a higher level episode represented by this pink square. And then the agent must, at a certain level of abstraction, it must match other sequences that were learned previously. So it may match several other sequences. So it discovers that it is currently doing this sequence and this sequence. And so when it matches previously learned sequences, the system proposes possible follow-up. So this sequence will propose this possible follow-up, and this other sequence proposes this other follow-up. And then we have to select one. So we need some criteria here to select a subsequent sequence. And then we'll have to re-execute this sequence. Because the agent cannot directly execute those higher level sequences, the agent only knows how to execute primitive possibilities of interactions, so those circles here. So that's where the self-programming effect lays. And then if the agent focuses on this higher level of interactions, then it can abstract even more from this level. So the same learning algorithms can apply to the abstract level to learn even more abstract episodes. So the same learning mechanism can apply recursively. So this is the general research domain that we are studying. We are not saying that we totally solved this problem. We only have preliminary algorithms that manage some form of this kind of learning, but it's not the full solution of this problem. So it raises many solutions. So if we look into details, let's see if I enact an interaction, the interaction A, and imagine then we enact interaction B, then we can learn the sequence AB. Just to memorize that I enacted interaction A, then interaction B, and the advantage is that if I enact again interaction A, then it can reactivate the sequence AB, and this sequence will propose to enact B. So I am in a context where I did A, so if that happens often, I learned that generally in this case I can try to do B. But again, it's an interaction, it's not an action. The interaction may correspond to the experience I'm trying to touch, with the fact that I am expecting that I will touch something, but I may be wrong. So in some cases, I may have enacted interaction A, which evokes interactions B. So B will be, for example, to bump into an object. But it might be wrong. I am anticipating that if I try to enact interaction B, it will lead to these results, but it might not be the case. Then imagine I do C here. So similarly, we can record the sequence BC. So if it happens often, then I will know that when I do B, I can do C. But that's not the only sequence we can learn. We could also think that what matters is not that I just did B, but I did AB before. Maybe doing B doesn't mean I can do C after, but if I do AB, then maybe most often I can do C after. So I should learn maybe A, B, C. But that's not the only thing. We could also imagine that when I enact A, most often I can subsequently do BC in a row. So I should learn A, BC to capture this possibility. Then I do D, and then here I didn't even try to draw the diagram. We see well that there is a combinatorial explosion. In fact, the number of sequences I could learn would increase exponentially with the number of steps. So here students note that we could also imagine that, for example, B doesn't matter. We should record that when I do E, A, then C, then I could do D in case in which B would not be significant. So we'd have also to record those kinds of sequences. So we are obliged to implement choices to be able to deal with this complexity. So how do we do that? So we need criteria for not recording everything, but we'll only record things that we expect will be useful. So for example, we can give values to interactions, and if some interactions have a highly positive or highly negative value, then we might focus on recording episodes that concern those interactions. So if we do that, we generate some kind of emotional behaviors. So when you look at the behavior of the agent, it looks as if the agent were only sensible to interaction that have high emotional valence and did not even notice interaction that don't have emotional valence. So any criteria we implement here implements a form of motivation in the agent. And then, so I did again B, and then we have another problem. So B could reactivate a whole bunch of sequences. So B might reactivate BC, BCD, and doing A then B will reactivate ABC and ABCD. So in every given context, many sequences can be reactivated. So we are again confronted to the problem of implementing a choice among all those possible interactions. So here, depending on the way we implement this choice, it will implement different form of motivations for the agent. So for example, if we choose a sequence that we didn't try before in the same context, then we will implement an agent that will look curious, tend to try other possibilities in the same context. So it's a way to implement curiosity. Again, if we give value to interaction and we choose interactions for that have positive values, that it will give a motivational flavor for liking certain interactions and disliking other interactions. And then we can choose an entire sequence. So, for example, in this context, I could choose a whole sequence, the sequence CD, for example. So now I am not on the base level timeline, but I am on a higher level timeline, the timeline CD. So the agent ignores how to enact the interaction CD. It has to enact first C, then D. But by automatizing the enaction of the primitive interaction and focusing on the higher level interaction, then we can implement an agent that can learn increasingly higher level of sequence. So if a sequence has a tendency to work well, then we will keep it and use it as a basis for higher level learning. So that's how we deal with complexity. It is as if it learned a more abstract interaction, and from that it can continue its higher level learning. But of course, we don't know if this interaction is optimal. It's just an interaction that works, and it gets used to it, and so it impacts its behavior. And another instance of agent that will discover other sequence will develop different kind of behaviors. So that's what explains the individuation of behaviors across different instances of agents. Okay, so that's what we are doing, and the exercise I am giving to you are designed to introduce you to this idea. So this led us to develop a new mathematical formalism, which contrasts with the traditional formalism. So the traditional formalization here, the agent receives an observation from the world. So it's implemented with a function of the environment state. And instead we develop this radical interactionism formalism in which there is no observations and actions, but there is only interactions. So the cycle does not start from the environment, but from the agent. The agent begins with choosing an interaction and says, I want to enact this interaction, which might change the world or not. And then the environment returns the interaction that was actually enacted. So here we do not think in terms of observations and actions or experience and result, but only on interaction. So for example, the agent wants to enact the interaction touch, but of course it will depend on the state of the environment. So I want to touch. If there is something in front of me in the environment, then I manage to touch. So the agent receives the interaction that it intended to enact. But if, for example, the agent failed to touch, then it will receive an enacted interaction which is different, which may correspond to moving in void and touching nothing. So with this model, we can then implement this recursive learning. So we have these primitive interactions that are hard-coded, and then the agent learns sequences of primitive interactions. So it constructs this set X that contains all the learned sequences of interaction. So then it chooses a whole sequence in this set X. So when it enacts this interaction, it in fact enacts the solid loop, all the primitive interaction. But for the decisional mechanism, it is as if it enacted the higher level sequence, and if it received the higher level enacted sequence. So with this, the algorithm can be entirely recursive, and the agent can reason in terms of higher level sequence and delegate to another part of the algorithm the charge of enacting the primitive interactions. So after a while, for the agent, it is as if it was interacting with a virtual environment that we call here environment known at time t, and which explains the fact that each individual agent sees the world in its own way. And we could not have this recursivity if we were not thinking in terms of interactions. So if you want to learn more, you can. It is published in this paper, an enactive cognitive architecture. So I'm not going into the details here, but that's what towards which we are tending. So the whole purpose of this course is to familiarize you with this way of thinking in terms of interactions. And then to implement the complexity of the agent. So this has been theorized by some researchers. The idea is to always think in terms of interactions, so maintain a form of balance between the possibilities of actions and the possibilities of perceptions. So for example, here we have this robot that is well balanced because it has few possibilities of actions, only 2 wheels, and here it is unbalanced because we added a camera which gives it complex possibilities of perceptions but not complex possibilities of action. And here if we add again possibilities of actions, it's balanced again because it has complex possibilities of actions and complex possibilities of interactions. So it's balanced again. So our idea to move towards more and more complex environments is to evolve jointly the possibilities of actions and the possibilities of perception. That is, in fact, think in terms of interactions. So that's what some authors call the problem of sensory motor coordination. And this has been theorized to understand how even a rudimentary algorithm like an insect or a fish or a reptile that have a very small brain, they don't have high computational powers. They cannot deal with complex problems with high combinatory issues. But those animals are not submitted to high combinatorial problems. So this approach helps understand how animals with weak computational powers can deal with complex world, because those animals don't even see the complexity of the world. So this helps us understand what we observe in rudimentary animals, the fact that they manage to develop non-trivial behaviors, even though they don't have a high-level computational power. So it's not a problem of that data reduction. It's a problem of constructing perception and actions from interactions. So I refer you to this article for this theory. Okay, so any question before we talk about the exercise?
Donc on va faire une petite pause comme la dernière fois et puis on va se retrouver en salle TP6 et TP7. Alors avant qu'on fasse ça, je vais vous expliquer un peu l'exercice d'aujourd'hui. Donc on va reprendre.
So before the break, let me explain the today's exercise.
J'ai mis en ligne un corrigé. Donc sur mon site web, il y a le corrigé de l'exercice.
So the solution of exercise 1 that we did last week is available online, and I hope it will give us a good start for the second exercise. So we had this exercise, so the agent had one bit of choice and then one bit of result, so it had 4 possible interactions. We had 2 environments, so I renamed them environment 0 and environment 1. So environment 0 is I do E1, I receive R1. I do E2, I receive R2. And the other environment, it's the opposite. And then we try different motivations by giving different values to interactions. And we want to design an agent that will learn to maximize its motivation without knowing the environment a priori. So I ask you to produce a report with activity traces. So the activity traces are quite simple. So in the first environment, it does E1, it receives R1, so it gets value 1, so it keeps on doing E1. But if we put the agent in environment 2, then it tries A1, it receives R2, and it's negatives, so it changes. It enacts A2, receives R1, and it's positive, so it keeps enacting A2. So I expect you to report those kind of traces. So here is the algorithm. So I explained it last week. So now the environment will return result R2 only if the agent alternates experiences. So we'll design an agent that is motivated to obtain R2. So I1, 2 and I2, 2 will be positives. So we have an agent that wants result R2. And it has to learn that it has to alternate. So if it keeps doing E1, it will receive R1. So it has to change doing E2 and receiving R2. And if it keeps on doing E2, it will get again R1. So it has to do A1, R2, E2, R2. And then change again, E1, R2. Then change again, E2, R2. And of course, we don't want to tell the agent that the environment is like this. So we want an agent that works either in environment 0, environment 1, or environment 2. We want an agent that works in any of the 3 environments. So this is the code of the environment. If experience at t minus 1 equals experience at time t, then result equals R1, else result equals R2. And to implement this agent, it will have to choose the experience at time t based on the interaction that was enacted at time t minus 1. So it's only a one-step context. So it will help us move toward this hierarchical learning of interactions. So last time we already had interactions that had an experience, a result, and a value. So we'll add two attributes, the pre-interaction and the post-interaction, to design composite interactions that are made of a sequence of a pre-interaction followed by a post-interaction. So this will allow us to organize them hierarchically. But so far we are only doing one level of composite interaction, but we prepare the ground for learning higher level. So our agent, so if at time t it enacted E12, it will reactivate E12, E22, because I12 matches that was enacted, and so it will propose I22, because it learned this regularity in this environment. And also it will learn that when it enacted I22, then it should enact I12. So it learned the association. I did that, I should do that. So it will work in any of our three environments, because in any case the choice to do is entirely determined by the previous choice. So at the end of time step t, we will record composite interaction made of interaction it minus 1 it, which are the pre-interactions and post-interactions of IC. So if IC does not exist, we add it to the set of composite interactions. And then at the beginning of time step t, we'll construct the list of activated composite interactions, AT. So it just did IT minus 1. It will look for all the composite interactions whose pre-interaction matches IT minus 1. And for each activated interaction, if the value of the post-interaction is positive, then it will choose this post-interaction. So try the experience associated with this post-interaction. So it knows that in the context in which it enacted this interaction, it can do the post-interaction. And if it's positive, it will try to do it. And if it's negative, it will choose another experience. Okay. That's it.
Donc commencez par aller sur mon site, j'ai l'exercice de la dernière fois et je l'ai mis en point jar et en point zip. Donc vous prenez
So you will find the solution of the previous exercise on my website, and then we'll work together on this exercise 2.